Hello everyone. Today we are going to learn about different sorting algorithms. So what is sorting? Assume that you have a set of objects, a sequence of objects. These objects are comparable to each other, so you can compare two of them and say that, okay, this one is smaller than the other one, or it is greater than the other one, or they are equal. Okay, so they should be comparable. Otherwise, you cannot put them in any order. I mean, in a sorted order. So the result of the input is a set of items, a sequence of items. We wanted to reorder these items so that the first item is smaller than the second one is smaller than the third one, and so on until you reach to the last item, which is the greater than every other item in this sequence. The sorting of a set of items, of a sequence of items, is a very popular problem in computer science and in many other problems that we solve. Just most of the times, as a pre-processing, we need to sort something, or we need to sort a set of items at some point. So that's why the problem is some of the essential problems in computer science, and we used it in many other places. That's why this is going to be a topic in this course, and we are going to learn about different algorithms for sorting, and see that what is going to be the best algorithm for sorting a set of items. So I'm going to just give you a short example here. Assume you have a set of items. Some of them are repeated. You wanted to just remove the repetition, just keeps the unique items. If they are not sorted, how you can do it? You should probably create another array, and for each item, just read all the items one by one. For each item, just check that if you have previously added it to the this output list or not. If not, you copy it and keep it here. Okay, so at the first item will be copied immediately. The second item that you check, you need to first check that if you have previously read it or not, if you have seen it or not. If not, you put it in the list. So you would check all the items, all the previous items in this output array. So it will be, for example, 5 will be stored here. If you take another item, you need to first check all the previous items that you have seen and stored, and if it is not repeated, you keep the item here. For the next item, you will see that one has been seen before, so you wouldn't actually copy it here. How much would be the time complexity of this algorithm? You can see that the time complexity will be theta of n power 2, and the reason is that it is possible that all the items would be distinct items, and so for the first item you would need one comparison. For the second item you need to check two items. For the third item you need to check 3 other items, and so on. So this is going to be the summation of all these comparisons. So in total, it would be the summation of I equal to 1 to n, that you know that the formula will be n to n plus 1 divided by 2, which is clearly theta of n power 2. Okay, what if the items are sorted? I mean, that algorithm that I mentioned was in the case that the items are not sorted. But if I have all this list of items in a sorted way, I can I can remove all the repetitions in theta of n. What is the algorithm? The algorithm, actually, we have seen the algorithm in week 2 when we talked about the time complexity. This was one of the algorithms that shows that we can solve this problem. We can remove all the repetitions from a sorted list in theta of n in linear time. You can see that this is way better than theta of n power 2. But now the question is that if the original list was unsorted, how much cost I would need to sort the items? If I wanted to actually go with this algorithm, I need to this algorithm here, the second algorithm, I need to sort them. This is going to be the topic of this lecture. We wanted to see that what is the best sorting algorithm, and if there are different sorting algorithms with the best time complexity, just see the difference between them. And interestingly, there are actually at least 3 sorting algorithms that all of them are going to have the best time complexity that we can get, and they are different. In different situations, you can use different sorting algorithms. So the whole topic here is to just discuss different sorting algorithms. Okay, before see the sorting algorithms, we actually make an assumption about the way that we write the algorithms. First, the input that we get, we would assume that this is all the items have been stored in an array. Okay, you can basically write down all the sorting algorithms for the linked list as well. But it is clear that working on a linked list is harder than working on an array, because accessing to different indexes in an array is constant time, so it makes everything much faster. So this is our assumption, that the input is given as an array, and at the end you should give the output as an array as well, either inside the original array, or you create a new array and return that. Anyway, we are going to work on arrays. Although the algorithms can be extended to work on the linked list, it just changed the some details of the implementation and how we, what is the final cost, because you know that accessing to different nodes in a linked list takes some linear time, not like array, which accessing to different indexes is constant time. The other assumption that we make is that all the objects that we work on are comparable. So they do have the method compare to. So if we wanted to actually compare 2 values, for example, inside the input array, for example, the item at index I, compare it with the item at index j, you because they are object, you cannot use the comparison operators, right? So how can I compare them? I can use the comparable method. I can write that, for example, a index I dot compare, actually this is little c, it was too much big for compare to a index j. If it is less than 0, it means that if it is less than 0, it actually means that ai is smaller than aj. If it is greater than 0, it means that a sub I is greater. If it is equal to 0, they are equal. Okay, so we are going to stick to these 2 assumptions when we are writing the algorithms in Java. So before actually checking the sorting algorithms, there are some properties, actually one property about the sorting algorithm which we care, and we want to check that different sorting algorithm does have this specific property or not. We would say that a sorting algorithm is performed in place, or a sorting algorithm sorts the input in place if the amount of space that it needs to sort the algorithm, in addition to the input array that you have actually the input stored in, that is just constant time, is just constant amount of space. It means that, for example, if you get the input as an array, definitely the input is going to be given as an array. This is our assumption, right? But you don't need to create some additional array depending on the size of this one. So if you are not creating an additional array, we would say that the algorithm is in place. But if you are creating some additional array, the algorithm is not in place. If you just need a couple of local variables in your in the method that you write, your algorithm is in place. And clearly, we prefer sorting algorithms that can be performed in place. Of course, we don't want to use more space. And we will see that some algorithms are in place, some algorithms are not in place. So based on the time complexity, we can divide all sorting algorithms to 3 categories. Some sorting algorithms that can be done in linear time, some sorting algorithms that can be done in n log n time, and some sorting algorithms that can be performed in n square time complexity. We also investigate the average case, worst case, and the best time case for the time complexity of different algorithms, and see that over different scenarios, the algorithm might have different behavior and have different time complexity. So those algorithms that works in theta of n power 2, clearly this is the worst time complexity among the 3 sets that we discussed, right? So they are going to be the selection sort, insertion sort, and bubble sort. Why we care about them? Clearly, you don't like the n power n square sorting algorithm compared to the case that if it is possible to sort the algorithms in n log n, so why we should care about the n power 2 algorithms? Actually, there are 2 reasons. First of all, some of these sorting algorithms are not good at all. They are really bad, so of course we prefer the n log n. But we are just studying them because of the fact that they have been done in computer science. They are a part of the history of computer science, and they actually helps us to learn how to analyze the best case and worst case time complexity. So basically, this is just for the sake of theory and learning. So the other reason is that one of these sorting algorithms, insertion sort, is very famous. The reason is that although the time complexity of insertion sort is in fact n power 2, but when the number of the size of the input is very short, something like, for example, less than 50 number of items, insertion sort is quite fast. This is very fast. This is even faster than those sorting algorithms that works in n log n. Although the time complexity n log n asymptotically is much better than n power 2, but in practice, if the size of input is very small, insertion sort is very fast. And this is another reason why we learn about these sorting algorithms in this category. The second category is n log n. These are the best sorting algorithms that you can get in general. This is going to be the quick sort and merge sort. You probably have heard about these sorting algorithms in some other courses, but we are going to just discuss them in detail and learn about all the details. There is another sorting algorithm which is also n log n, heap sort. This one will use a binary heap data structure. So we are going to discuss about this one as well at the end. So the last set of sorting algorithms are those that can be done in linear time, theta of n. So you might actually just say that why I said n log n sorting algorithms are the fastest and the best sorting algorithms that we can get. The reason is that linear time sorting algorithms cannot be applied everywhere. There are some specific restrictions over the input, and if you have those restrictions, you can use these linear sorting algorithms. So they are not applicable in general. That's why we are not going to consider them, and they are not going to be a part of the scope of this course. In the design and analysis of algorithm COMP251, you will learn about these linear sorting algorithms. So in this topic, we are going to cover the sorting algorithms that works in n power 2 and the sorting algorithms that works in n log n. Just one thing about the sorting algorithms. I mean, in terms of the time complexity, is that clearly the lower bound for the any sorting algorithm is going to be theta of n, right? Because if you are sorting n items, at least you need to visit every item once. So the minimum time that you need, the lower bound, is going to be theta of n. You cannot get anything better than this. But theoretically, if you don't have any restriction over the input, I can prove for you that the minimum time complexity of a sorting algorithm is going to be theta of n log n if we don't have any restriction over the input. But again, I'm not going to prove it here for you. We will discuss the proof in the course of design and analysis of the algorithms, COMP251, as a part of the corresponding lecture that we talk about sorting algorithm that works in linear time. We will also actually show that the lower bound for any sorting algorithm in general is n log n. So if we can find some sorting algorithm that works in n log n, this is the best thing that we can get. That's why I was emphasizing that this set of algorithms, merge sort, quick sort, and heap sort, are asymptotically the best sorting algorithms that we can we can implement. Okay, I'm going to stop talking about these theories, just jump into the sorting algorithms. We will first discuss about sorting algorithm that works in n power to n square time complexity.